organizers for putting this together. It's my pleasure to be able to speak to you about this today. So this talk is a sort of familiar story. We have a collection of nice schemes, varieties that are parameterized by combinatorial information. And we want to know how to arrange that information to get nice geometric properties. And along the way, we'll see some sort of familiar constructions or themes from the topic of toric degenerations. So just to fix some notation, I'll be working over an algebraically closed field, sometimes characteristic 0. N will be a lattice of rank M, and M will be its dual lattice. And T sub n will be the algebraic torus whose co-character lattice is our favorite lattice n. Sigma is a complete fan, and Y sigma is the toric variety associated to that fan. So the objects I'm interested in telling you about are vector bundles over this toric variety, which come equipped with an additional piece of information, which is an action by this torus T sub n. So the rank of that vector bundle will be R, and of course this is the dimension of a fiber of the vector bundle. And I'm gonna let E be sort of the generic fiber of the vector bundle. So you can think of this as the fiber over the identity point in the torus when it is thought of as an open subset of the toric variety. So in general, toric vector bundles, which is a vector bundle equipped with this action, appear naturally when you do sort of the usual geometric constructions of vector bundles from a toric variety. For example, the tangent bundle, or the cotangent bundle, or other tensor bundles. And it's straightforward to show that the tensor product of two toric vector bundles is a toric vector bundle, and the direct sum, and so on. So they form a nice category of geometric objects. And if you like, a running example for the talk is the tangent bundle of P2. Another large collection of these bundles comes from a familiar place of line bundles on toric varieties. So it's well known that if you have a line bundle on a toric variety and you equip it with a torus action, that these objects are characterized or classified by piecewise linear functions on the fan. So they have a nice combinatorial description, as do a lot of things with toric varieties. And so by that I mean a function whose restriction to each face of the fan is some linear function. And this linear function in some sense captures the structure of the representation of the stabilizer of the corresponding torus orbit on the line that lives above that orbit. So on P1, you can imagine these things as just a piecewise linear function on the line, and the slopes of this function over the positive part of the line and the negative part of the line are just the speed that the multiplicative group acts on the fibers over the torus fixed points on P1. So there's a nice familiar, one of the oldest stories in toric geometry, toric line bundles. Klyachko gave a classification of toric vector bundles in 1990, which also depends on some sort of information of the torus, but it's paired with information that I'll call linear data. It's an arrangement of subspaces in this fiber, this general fiber E. So this leads to the slogan that a toric vector bundle is linear data with toric data put together. So here's how Klyachko's classification of these objects goes. So for every maximal face of the fan, you give a decomposition of this model vector space labeled by the characters of the torus. So if you like, this is exactly describing the structure of a torus representation on the fiber over the fixed point. So it's a fixed point. So that means that the torus doesn't move this point around, it doesn't move the fiber around. So you actually get an honest representation, and we are simply giving the structure of that representation. So this is information that you attach to sort of the smallest torus orbits in the toric variety. And then you also, the second part of the characterization is information you attach to the almost biggest parts or torus orbits in the toric variety. So for every toric divisor, which corresponds, of course, to the rays in the fan, you give a decreasing integral filtration of this model vector space E. And you can think about this as something like the order of vanishing of local sections of the toric vector bundle along those divisors. So we have information over fixed points, we have information over divisors, and then the third piece of information is a compatibility condition, which says that if you have a ray contained in a face of the fan, then the filtrations corresponding to that ray, or the filtration corresponding to that ray, needs to be built out of the character spaces that you get from the first point for the face. And they can be computed by a nice inner product formula. And so, Klyachko says that every toric vector bundle yields this information, and if you give this information, you can build a corresponding toric vector bundle, and this is a one-to-one correspondence. And so this is Klyachko's classification. So just to give you an example of what this data can look like, if we take the tangent bundle of P2, the Klyachko filtrations corresponding to the rays have spaces that sort of come in three flavors. If you look at filtration level strictly bigger than 1, it's just the 0 space over each ray. If you take filtration level less than or equal to 0, then it's the whole space. And then at exactly filtration level 1, you get a one-dimensional subspace, which is just the line through the vector that corresponds to the ray generator. So you see there's some feedback here between the fan and the structure of the toric vector bundle, which is to be expected since it's the tangent bundle of the toric variety. And the second example just sort of illustrates how this information can look quite a bit more complicated. So this is a rank 3 vector bundle also over P2, and you can see that there's sort of 3 steps in each filtration space rather than the 2 in the tangent bundle. The spaces I'm really interested in telling you about are the projectivizations of these toric vector bundles. So the projectivization of a vector bundle, is a thing you can read about in, say, in Hartshorne. There's some nice exercises in that textbook on these objects. So if you like constructing things by taking proj, this is the proj of the sheaf of polynomial rings that you get by taking the sim series of the vector bundle. And geometrically, what this is the bundle of rank 1 quotients of the toric vector bundle. So if you go into a specific fiber, this is not taking the projective space of lines in that fiber. It's taking the projective space of rank 1 quotients of that space. And when one makes the definition this way, because it makes things work out a little bit smoother in the notation. So some nice facts about these spaces. We can compute the Picard group. All of the line bundles on these objects are obtained by pullback from the base, coupled with the sort of sheaves you get for free from taking a proj. We can also, in some sense, compute the global sections of these line bundles. This is just an application of the adjunction formula along with an exercise that says that the push forward of ON on these guys is sim n of the vector bundle. So this is nice because we can talk about global sections of line bundles on the projectivized toric vector bundle in terms of computations one does on the toric variety. And since everything in sight has a torus action, this benefits from the combinatorial techniques that you get in that setting. These varieties are smooth and projective over the field. So they're about as nice as you can expect. And one other interesting point is, if you take a a vector bundle of rank R and you tensor it with a line bundle, you get another vector bundle of rank R, and the projectivization doesn't see that. So, the Klyachko classification of toric vector bundles turns into just sort of a parameterization in this setting. There are many projectivized toric vector bundles with the same Klyachko data. Okay. So once again, we have a nice collection of projective smooth varieties here, parameterized by some nice data. And it's a natural question to ask, when do these things behave well geometrically? And so with that in mind, Herring, Mustata, and Payne asked, when is one of these projectivized toric vector bundles a Mori dream space? So as a reminder, roughly speaking, a Mori dream space is a variety whose total coordinate ring or Cox ring is finitely generated. So one takes a projective normal variety with a finitely generated class group. You select a generating set for that class group, and that allows you to define a Cox ring, which is like the universal coordinate ring of the variety. And you want to know, when is that finitely generated? And some nice things happen when it is finitely generated. It's a thing you want to know. So these were defined by Hu and Kiel, with an eye towards the Mori program. But they also have since found applications in other topics like arithmetic geometry. So this question has been thought about before, specifically for toric vector bundles. So it's a theorem that's about 10 years old now by Gonzales, that if your rank is small, in particular 2, then the projectivization of your bundle is a Mori dream space. So if your rank is 1, that is, if you're a line bundle, then the projectivization is just the toric variety itself, which are known to be Mori dream spaces. So it sort of says, if you really bound your rank and make it very small, then that constrains matters to the point where you get a Mori dream space. And then a follow-up theorem, also around the same age, is if you take the tangent bundle of a smooth projective variety, of a smooth projective toric variety, then its projectivization is a Mori dream space. And this introduces a very beautiful technique. That Hausen and Suess introduced a very beautiful technique to prove this. It uses a particularly nice quotient construction called the maximal orbit quotient. And roughly speaking, what's going on is your projectivized toric vector bundle is a Mori dream space if and only if it's this quotient operation, or this quotient is a Mori dream space. So an example that that fits both of these criteria is our tangent bundle of P2, whose projectivization has Cox ring, a quotient of a polynomial ring on 6 variables, modulo a very nice quadratic. And maybe after this talk, or after reading some of the papers by these authors, it's a nice exercise for a graduate student to try to say what the Cox ring of the projectivized tangent bundle of a smooth projective toric surface is. So more results along these lines. I'm going to say, this is my own terminology. It's not standard. I'm going to say a toric vector bundle is sparse if the dimensions of its Klyachko filtrations are very limited. That is, if, kind of like the tangent bundle situation we saw earlier, if the dimensions of the filtration pieces are either 0, 1, or everything. So Gonzales, Herring, Payne, and Suess show that if you have such a bundle, then its projectivization is a Mori dream space. Roughly speaking, because you have a lot of control over what that quotient is. This has also been shown last year, I believe, by Nodland using some different techniques. And this class of toric vector bundles subsumes both the rank 2 case and the tangent bundle of a smooth projective variety case. Another nice result of the same authors is that you can find a toric vector bundle whose projectivization has quotient isomorphic to the blow-up of projective space at n general points. And so by a famous result of Castravet, Tevelev, and also Mukai, that means that this projectivization is not a Mori dream space if certain numerical conditions hold, and this is related to blowups of projective space. Their results in blowups of projective space. So this says, there's some boundary here for these nice smooth projective varieties between the Mori dream space for toric vector bundles and the non-Mori dream space toric vector bundles, and we'd like to know more about it. And they also show, interestingly, that there's a smooth projective toric threefold such that the projectivization of the cotangent bundle is not a Mori dream space. So that's interesting, because, well, the cotangent bundle here is rank 3. So that already says that this question for rank 3 bundles is interesting. And it also gives an example of a toric vector bundle, namely the tangent bundle of such a threefold, which is a Mori dream space, whose dual, the cotangent bundle, is not a Mori dream space. So all of these results are sort of geometrically derived. So we wanted to figure out a way to view these objects in a more kind of algebraic and combinatorial setting. So that's what I want to tell you about next. So in order to tell you about the way we Kiumars and I thought about these toric vector bundles, I need to introduce a little bit of tropical geometry, but specifically of tropicalized linear spaces. So for a spanning set of our model vector space, so for all intents and purposes, just some spanning set of some vector space here, which we want to secretly think of as the general fiber of a toric vector bundle. I'm going to let L sub B, or B is the spanning set, be the ideal that vanishes on that spanning set. So it's just some nice linear ideal. And then trop L sub B will be the tropicalized linear space associated to this spanning set, or, if you're into matroids, the Bergman fan of the associated representable matroid. So, as a reminder, one way to obtain this set is you take all of the linear forms in this ideal, and you take weightings of the variables such that for any such linear form, the minimum weight appears twice.
What happens if you chose a different spanning set, actually?
Excuse me?
What if you chose a different spanning set B, essentially a different basis of the fiber of the vector bundle over 1?
Well, you would get a different tropicalized linear space.
Okay, so you're in a different chamber of the Tits building or something.
That's right. And in a moment, I'll explain.
I cannot hear you anymore, Chris. Hello?
No.
Okay. Chris, can you hear us?
Chris, if you can hear us, then please answer in the chat window, because we certainly cannot hear you.
So we have 2 times Chris here. Twice or not. No, I mean, there's one person here.
Apologies. So I think this is where I left off. Is that the case?
Page before, maybe.
Okay, so right, we have the tropical variety. It's the support of a nice fan, and I want to single out some special subfans of this fan. So the tropicalized linear space inherits a fan structure from the Grosvenor fan of this linear ideal, and I'm gonna use that to distinguish certain subsets. So I'm gonna say an apartment of this tropicalized linear space is a polyhedral subcomplex of the form that you get by intersecting a maximal face of the Grosvenor fan with the tropicalized linear space. So, this is just some union of faces of the tropicalized linear space, and each such set comes with a special basis, which is a subset of the spanning set we started with. So the term apartment is borrowed from the theory of Titz buildings, and there is a nice relationship between the tropicalized linear space and the spherical building associated to the vector space, and the apartments in this case are apartments. But for our purposes, it's just some union of faces of the tropicalized linear space. So an example of this, if you take the vector space of dimension 2 and just look at sort of the standard basis along with the negative of its sum, on the sum of the two members of that basis, the linear ideal in that case will be, the sum of three variables is 0, is a linear form that generates it. And the tropicalized linear space is just a union of three half spaces embedded in 3 space. And if you take the standard basis, the associated apartment is shown here in blue. It's these two specific half spaces. And any other choice of any of the other two choices of two basis members correspond then to the union of two other half spaces from this set of 3. And you can also notice here that the apartment is piecewise linear, isomorphic to a Q space of dimension 2. So with those elements in hand, I'm not going to give a definition of the data that we use to parameterize toric vector bundles. So I'm going to say a diagram for a fan sigma and a linear ideal L is an integral matrix with rows in bijection with the rays of the fan and columns in bijection with the elements of the spanning set that we talked about. That satisfies the following two conditions. So the first condition is that we insist that the rows of the diagram are points in the tropicalized linear space. So that means that if you take each row of this diagram, it's a solution to the tropicalizations of the linear forms that generate L. And so in other words, we can think of this as a configuration of points on a tropicalized linear space. The second condition is that we insist that this configuration of points satisfies certain closeness conditions. And I kind of think about this second point as a notion of combinatorial continuity. So roughly speaking, if rays in our fan are close together, we insist that the corresponding points in the tropicalized linear space are close together. So for every face of the fan, we insist that there be an apartment in the tropicalized linear space such that all the rows of the diagram that correspond to the rays in that face live in that corresponding apartment. So that's the second condition. I'm going to let delta here be the set of all such matrices. So this is, once again, a collection of matrices whose rows are solutions to some tropical equations, which satisfy some additional closeness condition that's defined by the fan sigma. And then we show that every such diagram is sort of it's not hard to show, but such a diagram yields Klyachko data, and so it represents a toric vector bundle. We also show that any toric vector bundle, for any toric vector bundle, you can find a spanning set, in fact, many, where the the corresponding toric vector bundle is represented by the diagram. So this is an over-parameterization of toric vector bundles, and therefore an over-parameterization of projectivized toric vector bundles. And then the last interesting point is that the set of these diagrams is the support of a fan. So, one could think about this as, you select a given linear ideal, your favorite linear ideal, and then you get this sort of fan of possible toric vector bundles, which are well related to that ideal. And then for different ideals, you could get richer or more restricted toric vector bundles. So examples of this, if you take the tangent bundle of P2, then as we've seen, the corresponding linear ideal is just the one generated by the sum of three variables is 0. The fan is P2's fan, and the diagram in this case will just be the identity matrix. And then as a richer example, this vector bundle that I showed the Klyachko data of earlier corresponds to a diagram for the linear ideal of these two forms in the y variables here at the bottom. And then, you have this nice 3x5 matrix. Okay, so why do this? So the upshot is that the diagram is information that gets us closer to a description of the Cox ring. So the way that works is that the Cox ring of a projectivized toric vector bundle is, as I guess every Cox ring is a nice example of a multi-Riesz algebra. So what that is if you have an algebra over your field, and you have a collection of integral filtrations, algebra filtrations of your algebra, then you can define an associated multigraded algebra by for any integer vector of length n, you just take the corresponding filtration spaces in each of your filtrations and you intersect them. And then the fact that these are algebra filtrations allows you to define an algebra operation on this direct sum, which makes it into a nice multigraded commutative algebra. And then, the question in this commutative algebra setting, which corresponds to, is your favorite space a Mori dream space, is, is your favorite Cox ring, or is your favorite, Riesz algebra finitely generated? So that's the kind of question we want to assess with this diagram technology. We're going to make a certain type of Riesz algebra and ask, how can we arrange our matters so that Riesz algebra is finitely generated? So here's how the Riesz algebra comes about. So if we're given a point in our tropicalized linear space, which lives in our favorite apartment A, then if you recall, that apartment has an associated basis. And when you give a basis of this vector space, what you do is you're given a recipe for writing elements of its sim series as polynomials in your basis. So if you have this point, this purple point omega, and you have an element f in your sim algebra, you think of your sim algebra as a polynomial ring in your basis, and that gives you specific monomials which appear in the expression for your element f. And then you just do the normal thing that people who study evaluations do when you're given such data. So when we want to compute a filtration level that our polynomial f lives in, we just dot our purple point from our tropicalized linear space with each of the exponent vectors in this expression. And then we take the minimum, and then we say f is in filtration level r if that minimum is bigger than or equal to r. So points in tropicalized linear spaces define, the nicest possible kinds of filtrations on the nicest possible kinds of algebras. These sort of combinatorially prescribed filtrations on a polynomial ring. Now, if we're given a configuration of such points, which is the data in a diagram, we get a multi-Riesz algebra given by a configuration of such filtrations. And then it turns out if you have any diagram representing your favorite toric vector bundle, then the multi-Riesz algebra you get from these types of filtrations for those specific row vectors in the diagram is the Cox ring. So one way to view Cox rings of projectivized toric vector bundles is they are the nicest, kind of the nicest possible multi-Riesz algebras of the nicest possible algebras. You get these very, very nice numerically, combinatorially described filtrations, and it's on a polynomial ring. And given this presentation, it's maybe counterintuitive that this could be infinitely generated at all. And so, if your diagram consists of row vectors that are sort of sufficiently close together, it will be finitely generated. And the infinite generation comes about from sort of the weird matroidal ways that these filtration spaces intersect as you go higher up in the filtrations. So then taking the question that we began this talk with and translating it, the question is, when does one of these integral matrices define a finitely generated Riesz algebra, or a Mori dream space? And moreover, what kind of set do the diagrams that behave well form? We have a fan here of possible diagrams. If you look at the diagrams that define finitely generated Riesz algebras, what kind of geometry does that set have? Is it just some strange spray of rays inside the fan? Is it some strange fractal set, or does it have more structure? So those are the questions I want to talk about for the remainder of the talk. So as a first approximation to answering those questions, Kiumars and I proved that there's a nice algorithm which is based on syzygy lifting in the theory of Sagby bases or Khovansky bases, which expands your favorite spanning set of your vector space to a finite generating set of the Riesz algebra / Cox ring if it exists. So that is, if you start with a diagrammatic description of your toric vector bundle this way, and you implement this algorithm, it will find a generating set after a finite number of steps, if there is one. It might take it 200 million years to do it. And you might be wondering, as a creature that only lives on average 85 years, if there's value in that, since the difference between 200 million years and infinite years is sort of small for us. But there it is. There is an algorithm which will find a generating set if one exists, and it's implementable in Macaulay too. So as an example of this, here's a diagram for a vector bundle of rank 3 over P1 cross P1, where the corresponding spanning set of 4 elements does not generate the Cox ring. But after 2 turns of this algorithm, we find 2 more generators, and that corresponding spanning set of size 6 does generate the Cox ring. And then you have to expand your linear ideal a little bit, as we see here on the right-hand side, and you have to expand your diagram a little bit, as we see here on the left-hand side. But this is then a Mori dream space bundle found by this algorithm. Okay. So it would be nice, though, to have more than just sort of an algorithmic description in terms of these diagrams of when we have a nice finite generating set of the Cox ring. So to tell you about that, I need to introduce one more piece of terminology, which is familiar from the theory of Newton-Kukov bodies, in particular familiar for people who are interested in finding valuations whose associated graded algebras are finitely generated. So this is the notion of a prime point on a tropical variety. So for an ideal and a point on the tropicalization of that ideal, we say that the point is prime if the associated initial ideal is a prime ideal. And once again, these objects come about when one considers toric degenerations of projective varieties that emerge from Newton-Kukov theory. So our first sort of broad theorem on the Mori dream space question using these elements goes as follows. So if you have a toric vector bundle with diagram whose rows are these omegas and whose columns are these alphas, you can define a specific map of polynomial rings using that data. And I'm going to let I sub B be the kernel of that map. Then we show that each row of the diagram can be padded by zeros to give a point on the tropical variety associated to that ideal. And then the theorem is that the image of this polynomial map is the Cox ring if and only if each of these padded points is a prime point. So this, not only shows that the given bundle is a Mori dream space bundle, but also produces a presentation of the Cox ring, if you like. And it's sort of this prime point feature that came from the theory of Newton-Kunkov bodies, which characterizes it. So what I'm going to tell you about next is a few applications of this theorem. So if we start with a linear ideal, there's a specific way that one can, and a diagram D rather, there's a specific way that one can take the diagram D and homogenize a generating set of that ideal to get a collection of elements in this ideal I sub B that I told you about earlier. And I'm going to call those the X homogenizations of our linear forms. And once again, this depends on the diagram and the linear ideal. And one can think about these homogenizations as sort of the desired or expected generators of this ideal I sub B. They're always in the ideal I sub B, but they don't always generate it, but we would like them to. So the theorem is that if you start with a fixed set of linear generators, then there is a finite locally closed polyhedral complex inside the space of diagrams such that a diagram is in that complex if and only if the Cox ring of the corresponding projectivized toric vector bundle is presented by these expected generators. So in other words, if you start with a linear ideal, you can, and a specific set of linear generators of that linear ideal, you can cook up a bunch of partially open or otherwise cones such that every diagram on those cones defines a Mori dream space bundle. And not only that, it defines a Mori dream space bundle with a very specific presentation of the Cox ring. So these are always complete intersections. And so that, these are particularly nice Mori dream spaces. So it turns out that some diagrams are always live in this complex for any choice of linear generators. So to describe them, roughly speaking, what you do is you take a matrix where each row has at most one non-zero entry, and then you're allowed to tropically multiply that matrix by any matrix of the form, any diagonal tropical matrix. So by that I mean an n by n matrix where the above diagonal and below diagonal entries are infinity, which is tropical 0, and the diagonal entries are integers. So you're allowed to take your diagram and multiply it by any such matrix, and all such diagrams will always live on this polyhedral complex F sub L. And these are in fact exactly the sparse bundles that I discussed earlier when talking about the work of Gonzales, Herring, Payne, and Suess. So these are particularly nice Mori dream space bundles that sort of always come about from this description. So these bundles actually have some nice geometric properties that I'll discuss briefly. So if we have a sparse projectivized toric vector bundle, then it ends up actually always being something called an arrangement variety. This is probably something that experts have known for a while. Arrangement varieties are nice generalizations of toric varieties that have been studied by Hausen, Hische, and Robel. And one can show that the Cox ring that you get from these varieties has a property called well poised, which was defined by myself and Nathan Ilton a while back. And what that means is that every point of this on the tropicalization of this special ideal that I discussed earlier is prime. So they're sort of they're by the theorem that I said earlier, they're Mori dream space bundles immediately, because every point on this tropicalization is a prime point, not just the ones that we need to check. And so in this case, general points of this tropical variety define global Newton-Akumkov bodies of these bundles and a lot of toric degenerations. And they're very nice toric degenerations. They can be described explicitly in terms of the diagram and this matroid. So other nice things that one can do with this description is, you can, as indicated or as suggested earlier in a question, you can, instead of placing a lot of conditions on the diagram, you can place some conditions on the linear ideal. So, we could ask what happens when we make the linear ideal as nice as possible, and that is we make it a generic linear ideal. So the corresponding matroid is a uniform matroid. Then this polyhedral complex that I mentioned earlier can be explicitly described basically as the set of diagrams with certain arrangements of zero entries. So the idea here is you take an integral matrix, you insist that certain rows have the same number of zero entries using a formula that I'm not telling you. And then you will always have a Mori dream space bundle with sort of generic geometric information. And a nice observation here is that if you take such a diagram and pad it with some positive integral entries, you always get another such diagram. And so this is a way to construct large combinatorial infinite families of Mori dream spaces. So an example of this is sort of the hypersurface case. If you take just a linear hypersurface with 6 terms, here is an example. Excuse me?
We could not hear you for like maybe 20 seconds. Can you just repeat the last 20 seconds?
So I think I was probably talking about this observation here.
Yeah.
If you take a generic linear ideals diagram and you pad it with some positive integral entries in a column, you get another such diagram. That's something that emerges from this combinatorial description. And so this is a way to build large combinatorial families of Mori dream spaces. You just sort of keep padding these diagrams and keep taking the corresponding generic linear ideals, and you get a large family of related Mori dream space bundles. So an example of this general case is just a hypersurface. And here we have a diagram which defines a Mori dream space bundle, and you see its Cox ring presentation here. And in this case, this description I mentioned of zero arrangements corresponds to the fact that any 2 rows of this diagram share a zero entry. And there's a condition like that for general linear ideals. And you can see here from the diagram, actually, that this is an example of a Mori dream space bundle where there are 4 steps in each Klyachko filtration. So you can build sort of toric vector bundles with many, many steps in the Klyachko filtrations that are still Mori dream spaces this way. And so to close, I'll leave you with a conjecture. So we hope to be able to show, or maybe someone can show, that this space of diagrams is the support of a finite fan with the property that the set of diagrams for which you get a Mori dream space bundle is a union of relatively open faces of that fan. So what we'd like to see is a combinatorial characterization of Mori dream space bundles in this sense. That is, you always can find some fan where the Mori dream space bundles, associated to that given linear ideal are a nice finite combinatorial set inside that fan. It would also be interesting, so we sort of proved a special case of this with these bundles I discussed earlier. where we take these expected, where to go? These expected homogeneous generators. So it would be nice to know, if this polyhedral complex here has a natural geometric interpretation. Perhaps it's part of some tropicalization of something like that. So I apologize for the technical problems, but I think I'll finish there. And thank you for listening.
Yeah, let's thank Chris. And well, now we have a lot of time to ask him questions. Please feel free to speak up or write in the chat.
So one of the places where these possibly multi-created Riesz algebras show up is when you look at blow-ups.
Yeah.
Right. Can you say something about that case? I mean, is your theory applicable to?
Yeah, I mean, I should say that, like, this this characterization, that this sort of primitive theorem here doesn't really depend on you working with a polynomial ring or a projectivized toric vector bundle. It's sort of,
that's what I thought. Yes, that's why the question.
Right. So there's sort of a prime point characterization for any algebra you want to put in place of sim E. And that's a natural thing to ask, like, yeah, I think the answer is yes. If you have a sufficiently reasonable description of what you're blowing up, you could try
points in P2, nothing more.
Well, then I think you actually can view it, I believe, by work of Gonzales, Herring, Payne, and Suess as something very closely related to a projectivized toric vector model, and probably you could just use these sort of techniques on it.
Except when I blow up 9 or say 10 or more points, then things get out of hand.
That's right. And what will happen in that case is, this algorithm won't stop, and you won't be able to find an ideal like this where this prime point condition holds, right?
Okay, so is there any way to relate your chamber decomposition with the Zariski chamber decomposition of, say, blow-ups of P2?
I would hope so, but I don't know at this time. but I imagine if you take sort of any sufficiently reasonable variety and embed it in some toric variety or some family of toric varieties, there's some kind of fan like this that describes those behaviors, and some subcomplex that describes the nice part. And I'd love to hear about that story and think about this.
Say if you take like a Mori term space and you embed it into a smooth toric variety by the Hukil embedding, I mean, that would be your model situation.
That's right. That's right.
Okay. And
in that case, my guess is you could replace sim E with like the coordinate ring of the open part, and then that would this map would then be the corresponding embedding of the open part into the torus.
Mm-hmm. Okay, well, thank you.
Okay, let me ask a question as well. Can you go to that conjecture you stated in?
Yeah.
Just to be sure to understand, do you think that sort of the locus for which the conjecture is true, is it going to be open and dense in this fan?
No, I would just I mean, it would be cool if someone could prove that, but I suspect it's not.
Okay.
The way I'm imagining it is, there's some cell decomposition of this set, and then sort of walls and lower dimensional objects in that cell decomposition correspond to the nice behavior, and in general you have kind of bad behavior. But once again, this is sort of open territory. I don't know what it will look like. The best I can do at this point is just point to this complex we described in this complete intersection case, where it's some lower dimensional subset of the space of diagrams, but there could be more, right?
Yeah.
So I should say that the diagram as you change the diagram, you change the ideal quite drastically that I sub B. So it could be the case that, like, you know, your ideal is generated by many more forms than the ones I gave. And for that matter, the same sort of technology could apply for higher degree generators as well. So yeah, I mean, I imagine that this conjecture, you know, could lead to some nice finite behavior, or maybe it's some bad behavior. I don't know.
Okay, let's give people another chance to ask